Welcome in, everybody. Thank you for joining. Get yourself ready with a notebook, a pencil, or a pen. Anything you choose to write with is fine. This is math from the void. Math coming at you out of nowhere. And today we have a problem from decades ago, from the 1989. Jeez, it's like 3.5 decades ago. 1989 Calculus AB exam. This problem is intended to be done without a calculator from what I can tell, so we're going to do it without a calculator. And as usual with these area and volume problems, it's good to get an idea of what the region looks like. So these are just some basic boundary curves from pre-calculus or even Algebra 2, really. So you can imagine, and the y-axis. So you can imagine what this region looks like. Something like this. Square root of 6x plus 4. You could also think of that as square root of 6 times x plus 4 over 6, or x plus 2/3. And so that's going to give us a point here at negative 2/3. If you plug in 0, you simply get the square root of 4, which is 2. Okay, so something like this. And then we're going to have the line y equals 2x as a boundary as well. Like that. And the y-axis is also a boundary. So you can see that the region is only this part in the first quadrant. Okay? And there's some kind of intersection point which we can find. So that's what I advise for setting up your visualization. If you don't already have it crystal clear in your head, if you have it crystal clear in your head, you don't have to use the time. And from now you can give yourself about 12 minutes or so to go ahead and solve this problem on your own. Yeah. Gotta fly on your own first, little bird. Then you can come back, unpause the video, come back and see how we do it here. Okay? So let's get started. Find the area of R. Well, I have some clear boundaries on the top and the bottom, so I'm going to take advantage of integration dx. That's going to be the integral from a to b. Well, my a value, my starting value is 0, but my stopping point, this x value, I'm not exactly sure what that is. So I can figure out what that is by setting these two things equal to each other and solving for x. Alright, let's square both sides. So we have 4x squared. And let's also move the 6x over, as well as the 4. Okay, now this reduces to a pretty nice polynomial, 2x squared minus 3x minus 2. So this is pretty easy to figure. We have 2x and x. We have, what would that be? Minus 2 and plus 1 here, I believe. Okay, so we would have some theoretical intersection. If this thing were to continue, we'd have intersection back here at negative 1/2, but otherwise we're going to be looking at x equals 2 as the true solution. And you can plug that back in to see that 2 works, negative 1/2 doesn't work. So this is our stopping point, and we're going to integrate top function minus bottom function. On top is the square root. So in fact, I'm going to write this as 6x plus 4 to the 1/2 power minus 2x. Okay, and this is pretty simple. You could do a U-sub, but it's not really necessary. You'll just want to make sure that you have 1/6 sort of accounted for. This is going to be 3 6x plus 4 to the 3/2 And so this is going to be, well, if I have 1 over 6 times 2 over 3, my apologies, we're going to get 1/9. And minus x squared, pretty straightforward there. Now this is all going to be evaluated from 0 to 2. And 0 is usually a really nice number to plug in where nothing important happens, but something does still happen in this case. Let's plug in 2 first. That's going to give us 1/9 of, 16 to the 3/2. That's a pretty nice number. Minus 2 squared, which is 4. And from that, we're going to subtract 1/9 of 4 to the 3/2. That's also a pretty nice number. And then minus 0, so I guess we don't even have to write that. Okay, well, 16 to the 1/2 is 4. So to the 3/2 is 64, so we'll have 64 over 9 minus 4. And then here we just have 4 to the 1/2, which is 2. 2 cubed is 8. So we're going to have 8 over 9. And that's going to give us a grand total of 56 over 9 minus 4 over 9, which I might as well call 36 over 9. Yeah, sounds about right. So that's going to give us 20 over 9. And that is the area inside of this graph, or inside of this region, rather. Okay, not so bad, not so bad. Part P. Set up, but do not integrate, an integral expression in terms of a single variable, and we're revolving R around the x-axis. So it's important to note here that because we're not revolving this around one of the boundaries, we're going to get some washers. All right, so what this shape is going to look like. Let's erase, not everything. Let's erase some of the stuff that's in there. And we can three-dimensionalize this. There we go. There we go, and kind of back there. And we're going to rotate this around the x-axis. So we're going to get these washers because the outer boundary is created by the further boundary, I should say. And then we have the hole in the middle, which is created by the inner boundary. So if we take a look at those cross-sectional areas, where the center is the x-axis, this distance is little r, and this distance is big R. Now the big R is going to be the distance from the axis to the furthest boundary. So that's from 0 all the way to square root of 6x plus 4. And the smaller ring is going to be, the smaller radius rather, is going to be simply from 0 to 2x, which is just 2x. So the area of these cross-sectional slices given by pi big R squared minus little r squared. Really, that's just pi big R squared, but then minus pi little r squared, because we're just taking the area in between these circles. And so if we express that as x, this is simply going to be 6x plus 4 minus 4x squared. So therefore the volume, I guess I'll put it down here. We don't have to evaluate it, we just need to write the integral. It's going to be pi times the integral from 0 to 2 of negative 4x squared. I just chose to write it in like descending order, but you really don't have to do that. Dx. There we are. That'll give us the volume of that solid. Pretty straightforward. Pretty straightforward. We just need those cross-sectional slices, and then it's very clear. So make sure that you know whether or not it's going to be a washer or a disk setup. Speaking of which, set up, but do not integrate, an integral expression in terms of a single variable, again, but in this case, we're going to be revolving around the y-axis. So you'll notice that in this case, we're going to want to look at things dy, but also, because the y-axis is vertical line, but also the y-axis is one of the boundaries, right? That is one of the boundaries. So we're going to end up with disks, not washers. In fact, before I three-dimensionalize this, let's draw the boundaries really quickly. We have that, and then we have something that's coming through there. That seems good. Here is the pole, and then we'll three-dimensionalize this. So what are these slices going to look like? They're just going to be straight up discs that go around the y-axis. The thing is, once we get to a certain height, you'll notice that the right boundary and the left boundary, well, the right boundary doesn't change, but the left boundary does. So for the first amount of discs up to this point, these are all, I'm going to call them purple discs. But then, after that point, the right function minus the left function is 2x, y equals 2x. And then on the left side, I know it looks weird to call that the left side of the boundary, but on the left side of the boundary, this is going to be the square root function, y equals square root of 6x plus 4. So we have to be careful on how we describe this volume, because first we're going to have some discs, and then we're going to have washers on top of it. Got it? Yeah, so what those washers are going to look like, and they're not going to start until we get to the top of the discs, which is at y equals 2, by the way. Once we get to y equals 2, we're going to have these shapes which go around according to the 2x, but then they have a hole in it according to the square root function. All right, so let's take a look at these cross-sectional slices for the first chunk of area. That's going to be with the y-axis as the center point. And the only radius here is going to be whatever the x value is. So we have to convert the equation y equals 2x. We have to convert that into x equals 1/2 y. And so the area of each of these discs is pi times 1/2 y squared, or 1/4 pi y squared. And therefore the volume of that piece is pi times the integral from 0 to 2. Again, that's where this sort of boundary, the y-axis boundary, it cuts off, and then it's no longer the boundary. After we get past y equals 2, the new boundary is the square root function. So from 0 up to 2, we're going to have 1/4. I guess I should take the 1/4 out as well. Just the integral of y squared. Now that's only this bottom portion. So let me just be really clear on what that is exactly. That's just the bottom portion which caps off right here. All of those are discs. But then once we get past that point, now we have a different boundary. So we're going to be wrapping this around with washers now. So our second set of shapes are going to go like this. We're going to have the outer ring, we're going to have the inner ring, and then we're going to have the center, which is the y-axis again. So here's our little r, here's our big R. But how do we describe our big R? That's still just 2x, which means in terms of y, it's 1/2 of y. But with this smaller r, we're using the equation y equals square root of 6x plus 4, which means x equals y squared minus 4 all over 6. And so the cross-sectional areas of these slices is going to be pi big R squared minus little r squared. And that's going to give us pi times 1/2 y squared minus y squared minus 4 over 6 squared. It's kind of an ugly expression, but it's not too bad. We just have to write it in. Now the question is, from what y value to what y value do we add these up? Because how high does it go where these meet? These meet at y equals 4, and you can check that because we know that they meet at x equals 2, so that means the y value has to be 4. So this is going to be the integral, well, I guess I can say pi times the integral from 2 to 4 of 1/4 y squared minus, I don't really need to work all that out. You could just leave it like that, but I'm just going to do it anyways. 1/36 y to the 4th minus 8y squared plus 16 dy. And so the total volume is going to be combining those together. I guess I can just sort of say like total volume is 1/4 pi integral from 0 to 2 of y squared dy plus, I could have factored out 1/4 pi and all this stuff, but you really don't need to do all that. Pi times the integral from 2 to 4 of 1/4 y squared minus 1/36 y4 minus 8y squared plus 16. And so yeah, if you wanted to, you could, combine these in a way, but it's a little less messy to do it like this. Remember, we don't need to evaluate this, although we could. It's not the hardest thing in the world. We just need to set it up, and that's why this problem is a little bit easier. It could be done without a calculator to integrate that, but there's plenty of work done already for this problem. Okay, so that should do it. If you're comfortable with setting up your cross-sectional areas, you'll have no problem solving these area and volume free response problems. Make sure that you understand if it's going to wrap around one of the boundaries, it forms a disk like this, versus if it's wrapping around a line which is not one of the boundaries, you're going to get some kind of a hole inside, so you get this washer shape. Alright, I think that's enough blab out of me. I'll see you guys next time in the void.